let's say it's draw a line here. Our focus is going to be on distributed consensus and an important result from distributed systems called FLP impossibility, which shows that even if you have one faulty process, it is impossible to actually reliably ensure consensus. So this is a result from the FLP's names of the authors who proposed this results of Fisher, Lynch, and Patterson. So I think this was from 1985. It's a landmark result in a distributed systems field, right? So first of all, what is consensus? Anyone?
Agreement, where all parties agree on a particular fact.
Right. So consensus is essentially you have computation happening on multiple nodes. Let's say this is R1, this is R2, and this is R3. Right. So you want all the nodes to essentially agree on something, right? So some value. So for instance, the most common use case is when you have a transaction, right? So there is a transaction that happens. Right. So, and this is a distributed transaction. So you want all the nodes R1, R2, and R3 to either commit the transaction or abort it, right? So you have two results for the transaction, either committed or abort, right? And for the state to be consistent, you want all three, in this example, all three nodes to agree on either committing the transaction or aborting the transaction. You cannot, you do not want to end up in an inconsistent state wherein, let's say, one node has committed the transaction, other two haven't, right? So this is some sort of a common use case of where you actually need some agreement, some consensus among all the nodes that participate in your system, right? Good so far? Okay, so this is essentially, a typical use case for, let me write it down clearly. So transaction commit, which is a typical use case for consensus, right? Okay, so you want, so let's say you have a program P. Let's call it something. Okay, let's say you have a program P, right? Which say, which is essentially a consensus program, which guarantees that given any number of nodes, you are going to, if multiple nodes, are competing, are trying to get an agreement, it guarantees that essentially agreement will be reached, right? So let's say you have such a program P, right? So what do you need from that program P, right? So this is consensus program, right? So you want essentially multiple conditions. The first being that a value, a decision has to be eventually reached. Right, a decision has to be reached eventually, right? And what else do you expect from the process P, from the program P?
Some result.
Yeah, so that's the decision, right? So P has to eventually terminate and give you a decision, right? And when the decision has been achieved, so essentially every pair of nodes has to agree on the decision, right? So that's because you need consensus, right? So you need agreement, right? So agreement. And what else do you need? So a decision has to be something that is proposed by one of the process, right? You can't just arbitrarily come up with a random value, and you can't game the system and return, let's say, 0 all the time, right? So decision value has to be proposed value. Like for instance, if commit or abort, right? So decision value has to, has to be one among commit or abort. And one of these, if let's system reaches commit as a decision or abort as a decision, then it must be the case that there must be at least one process, one node that has suggested that value, right? Otherwise, you could come up with a trivial solution for P, wherein you say, regardless of what a transaction, all the transactions come, and I'm going to abort all the transactions, right? So all the nodes, you're always consensus value is always aborting. So that would serve as a trivial sort of solution for P, right? You don't want that, so you want to avoid that, saying, okay, so whenever a node proposes, whatever value gets decided, it better be the case that there is at least one node that actually proposes this value, right? Okay, so these, let's say we have these requirements, right? So these seem to be sufficiently strong requirements for a consensus process. So now we ask the question, is this such a P ever possible? Is it ever possible to conceive such a consensus program P that satisfies these conditions, right? So recall from our first lecture and second lecture, what is the defining characteristic of a real-world distributed system, an asynchronous distributed system?
Failures.
Failures, right? So you have failures. Failures are not an exception; they are sort of norm. So when you have a failure here, when you take failures into account, so that's when you actually want to answer this question. Given that processes are faulty, things can fail. Can you construct a program P that lets you perfect consensus among all the participating processes or nodes? So that's the question, right? That's the key question, which FLP paper answers in negative, right? So FLP, the key result is that such a consensus is, or let me write it down, right? Distributed consensus is impossible with one faulty process, right? So even if one node crashes, or if there's a possibility that one of the processes can crash or one of the nodes can crash, then FLP result essentially says that you can never have a program P that terminates and gives you the result. You can never have a consensus algorithm. So that's the key result. This is the FLP theorem, right? So that's the key result that we're going to discuss today, right? And actually, we're going to go into the proof of FLP theorem. But first of all, let's appreciate what the magnitude of this result, right? So essentially what FLP theorem says is you cannot have regardless of whatever you do, right? So when you have an asynchronous system where each machine is running on a different clock, when there are failures, when the failures are possible, right? And you have, let's say, a distributed database that is running on this setup, right? So which essentially means that you can never have consensus among these processes. When you cannot have consistently commit or consistently abort result for a given transaction, given that there are failures that are possible in the system, right? So that's the that's sort of in the context of at least the most real world applications, which include transactions. So that's the implication, right? Okay, so any questions, any comments on the statement of the theorem so far?
Yeah, I have one question. So does
Right.
the theorem only applies to asynchronous system, or does it also apply to synchronous ones?
Good question. So for synchronous systems, actually, there are results that show that you can, in fact, even with Byzantine failures, you can achieve consensus. But I know of the existence of such results. I have never really looked at those results, so I don't know how exactly they're proven though. But it's conceivable, because when you have a synchronous system, essentially you can make assumptions about this clock skew and the time in which things happen, right? So you can make assumptions about how long a process can take, etc. So it's conceivable that it's the consensus problem is solvable there. Okay. Any other questions? Okay, so if you look at the theorem statements such as these, right? How would you even begin about proving these statements? Like if you look at that, I've actually written it down in English, right? So I didn't actually say, it's not like a Fermat's last theorem or Pythagoras theorem that you can just simply have a statement and start from first principles and prove. Seems to be a very vague statement. So how do you go about, how do you even begin to actually prove this sort of these sort of results, these sort of a very high level sort of on results that are verging on the border of philosophical about the distributed systems, right? So that's that's what we're going to look at today. So often you have this landmark results in this particular class we're going to focus on distributed systems, but there are also other lot of results that speak that sort of border on philosophical and various fields as well, which appear to be huge and vague, right? So how do you go about proving those sort of theorems? Okay, so to prove any sort of this sort of vaguely stated theorem, what's the first thing that we'll have to do? So you have to essentially show what we mean by when we say distributed consensus is impossible with one faulty process, right? So there must be a way of precisely speaking about what is a distributed consensus and what is a faulty process and what does impossibility mean, right? So okay, so for that, what do we need? What would be the first step to do in let's say if you want to, you are the ones who are going to set up setting about to go this sort of prove this sort of a theorem, right? What would be the first step that you would do?
If I had to guess, maybe you define some sort of failure, what it means, it kind of like a base case that we'll end up coming back to.
Okay, so you need to define failure, yes. But also, first of all, you need to give precise meanings to each of these words, right? So what is consensus and what is a system? When you want to prove something on a distributed system, you need to actually write down what a distributed system is, right? And since theorems are, we prove theorems in math, so you essentially need to state, you need to have a model for a distributed system, right? You need to have the very first thing that you want is for the real world system that you are trying to prove theorem about, which is in this case an asynchronous distributed system. You need to have a sufficiently expressive mathematical model that captures the complexity of this real world thing, which is a synchronous distributed system, without having to talk about nuances, all the, for example, in the case of distributed systems, we don't have to talk about sends and receives and every minor detail, right? So you have to sufficiently abstract the system in mathematics so that you can preserve all the behaviors, but it is sufficiently abstract that you can talk about things in a sufficiently abstract level, right? Okay, so let's go about doing that. So we need a model for distributed system. Okay. Okay, so let's consider our previous, so let's say this example. Copy. Okay. So let's say we have this system, right? What are the components of the system? Okay, so we have 3 nodes. So basically 3 processes, R1, R2, and R3. Let's call it P, right? Set P. So when, the first thing that you want to model is essentially the nodes of the distributed system itself, right? So that's the first thing. And what would the process, what is a process, right? So R1, R2, R3 here, I mean, these are nodes, but I'm speaking of them as processes because they actually do some sort of computation. So you have control on each process, and there is a communication between process and process, right? So you need to model control and communication, right? So let's look at communication first, right? So okay, you have, let's say you have, you modeled 3 nodes using 3 constants, right? R1, R2, and R3. So let's say these are variables or constants in mathematics, and you want to model the message that R1, model the event that R1 has sent a message to R2. right? Or another event, for instance, that R2 has, so let's say this message is M, has consumed the message M, right? So how do you go about representing these sort of events in mathematics?
Is it by defining a relation between R1?
Great. Yes. Great. Yeah. So you have, let's say you have, you want to define a relation, right? You want to define a relation, right? Relation between what?
The set of process and the set of process. So if P cross P,
Let's call it T. Okay. It's between P cross P
and M, the message, the set of all messages.
Okay. Let's say M is the set of all messages. Okay. So P cross M.
Yeah.
Okay. So you want to, okay. So a send event you want to capture, let's say from R1 to R2 as R1, R2, and M.
Yeah.
Right.
Yeah.
So that's what you want. But R1, R2, and M, where do you want to put it? So essentially you have to, system has moved from, initially there is a system where R1, R2, and R3 exist and nothing has happened so far, right? Now some event has happened wherein R1 has sent a message to R2, the message is M, and you quite correctly said that you can model this message as R1, R2, and M, right? Now you have to represent this new state wherein this message exists, that is in transit from R1 to R2, a message called M. How do you represent that? So that's where you have to you actually, in order to represent these sort of things, you actually think of system as moving from one configuration to another configuration, right? So you think of, let's say let's define this as possible. Let's say you have R1, the three processes, the set of processes R1, R2, and R3, right? And let's say each process, let's keep things very simple for a while. Let's say you have a message buffer, right? Which is initially empty. So this is set of processes, let's call it P, and this is message buffer, right? So initially, let's say I'm only modeling network messages and nothing else, right? I mean, sends and receives essentially, sends for the time being. So you have initial configuration, which is just a set of process R1, R2, and R3, and message buffer, which is initially empty. And you can think of this message sending as being an event that takes this configuration to message process being the same and a new message. So since you have message buffer, you're putting a message in a message buffer, right? So let's say you drop the sender part because you don't need it. It's essentially you only need the receiver to actually deliver the message. So let's say R2M, for instance. Does that capture the send event to the extent we want? Prashant, does this look good? Like for your for the use case that?
Yeah, so I was wondering, why did we, so in the message buffer, why did we just represent it as R2M? Why did we not want to know that?
Well, you can also do that. Yeah,
Okay.
sure. R1, R2. I mean, this is also good. This is also fine.
Okay.
Well, I mean, I'm trying to set the stage for consensus, because in the consensus you actually don't know. When you get there, you actually don't really care about the sender, so it's not needed.
Okay.
But let's say, I mean, for the sake of this example, yes, you can in fact put R1, R2, and M. So that sort of captures what happened here as a relation, as a this is what you call as I call as transition relation, right?
Okay.
So you define a relation. So I defined here, but let me erase that there. This is because there we have used it for messages, right? So you define a relation called transition relation from one configuration to another configuration, right? And configuration, for the sake of this particular example, you have defined it as essentially a set of messages cross or P cross message buffer. So a system processing an event, such as generating a send event, for instance, can be captured as transitioning from one configuration to another configuration, which in mathematics, you just simply represent it as saying that, okay, my transition relation contains one tuple from R1, R2, R3 empty set to R1, R2, R3 with a singleton set containing R1, R2, M. So far, so good? Okay. Okay, good. But messages processes just don't only send messages, right? So what do you have? First of all, in each process, when it sends, it sends a message, but then also there are processes that receive the message and actually process the message, do the local computation, and maybe send few more messages as a response, right? So you essentially have a system wherein these things are happening, wherein at any given point of time, process can, for instance, seek a message, get a message from, do some local computation, generate more messages, and put those messages back in the message buffer, right? And you can envision this happening over and over again for a distributed system, right? So that sort of captures, at least to some extent, what is happening in a system, right? In a system like the distributed system, abstractly in mathematics, right? So that is the fundamental, that's the basis from which we are going to start. In order to prove a system, a result such as distributed consensus is impossible with faulty process, you need to start defining what a system really is in mathematics. And the best way to represent event-driven systems such as distributed systems is essentially as transition relations, right? You define, you abstract each of the objects into these variables R1, R2s, and R3s, and then you define these transition relations, saying, okay, here's a relation that defines, that precisely captures my system, what my system does, right? Okay, so far so good. Okay.
And so what you're saying is, in this case, when we are defining the configuration, we need to represent the configuration. So the configuration space is something we are designing, and we say that it consists of the set of processes and a fictional notion of a message buffer, because the message buffer does not really exist anywhere, right?
So yeah, good question. So here is where abstraction comes in, right? So you distributed systems engineer will come back and say, hey, when I implemented the system, there is no such thing as a message buffer. When R2, I'm just sending a message, it goes over the network, it goes to R2, and R2 processes, it keeps it in its internal system, or basically processes it. There is no such thing as a global message buffer. But why do you have a message buffer here? Right? So the answer to that question would be like, you don't, as long as you model the system property, the system behavior correctly, your abstraction could be anything. Right? You can conceive of new artifacts in mathematics to model the events that are happening in your system. Right? They need not correspond to concrete artifacts in your actual implementation. But as long as that helps you capture what's happening in the system easily, in a simple fashion using simple mathematical artifacts, you're good, right? So in this case, for instance, of course, there is no such thing as message buffer, but consider this scenario wherein you actually send a message, R1 sends a message, but R2 hasn't yet received it, right? So it is somewhere in the network. So you model that essentially as imagining there's something called message buffer, which essentially abstractly models network, where that message stays in as long as it's needed, right?
Yeah.
And how do you model, for instance, the fact that R2 has tried to receive the message, but it hasn't yet received it? So you, for example, define a transition that says you can always go from message buffer containing message M to a new configuration where message buffer still contains the message M, although R2 tried to receive it. Which means that R2, despite the attempts to receive the message hasn't yet been delivered. That is something you can model it by defining a transition from existing message buffer state to the same message buffer state, right?
Yeah.
Okay, so this is essentially the trick sort of we play to represent the physical events such as message transmissions or node crashes, etc., to in mathematics, right? Because essentially you have to precisely capture the behavior of your system in mathematics in order to prove theorems about it. And this is sort of a tricks that we play over and over again. The common way to model a system is essentially as a configuration, defining what exactly configuration is using mathematical objects such as functions and relations, and then defining transitions between these configurations. That's the same trick we're going to play to prove FLP theorem as well, right? So let's draw a boundary here because things are going to get a little more involved, a little more concrete now. Okay, so we want to model a consensus system, right? I mean, the system where consensus executes, a distributed system where consensus protocol executes. So what is it that you want? So again, you have a set P of processes, right? So let's say you have processes P1, P2, P3, and so on, right? Okay, for the sake of example, just leave it P3. Okay. So you have the processes, right? Now, what do you need to keep track for each process? So, as I said, a consensus protocol is one where a process proposes a value, and eventually each process decides a value, right? So you can think of, let's say, defining a value called xp for a process P, which is P's proposal, and a value called yp, which is essentially P's decision, right? Good. Okay, so when you're defining then a configuration, you want to, for a given, when you are capturing the state of a process P, you want to capture xp and yp. That's for sure, because you want to, you want to capture the transitions wherein the value, let's say process 2 proposes value commit in case of commit abort, and eventually it decides to abort because some other machine did not agree also. So you have two values, xp and yp, which you can think of as, let's say, input and output. Right? What else do you need? So each process does some sort of local computation on receiving a message or something, right? So essentially it has its own local control flow. So let's say you model it using its own program counter or P. Let's not worry about what program counter is yet. It abstractly, it intuitively corresponds to your program counter notion in C and operating systems, right? So you have a program counter. And of course, you have a memory at each process, right? So you have each process can remember things because it has its own memory. So it can have, for example, think of it as local storage for P, right? Okay, so you at least need these things to talk about, the state of a process P, right? And since the system is essentially a collection of, P processes, you can think of system state as having, let's say, represented by capitals, right? X, Y, P, and ST, where these are arrays or partial functions instead of single values, right? So what you say is, how you define them is, let's say this: define X as a function or partial function from P. Actually, when you have P, it's a complete function. Okay, function to consensus values, commit or abort. Let's represent commit using 0 and abort using 1, right? So you can have 0 and 1. Okay, so which means that when xp, let's say x2 is 0, how do you interpret that? You interpret that as essentially saying that process 2 is proposing to commit the transaction, right? Yeah, so you have you essentially define the system state as consisting of, let's say, 4 things. First one, X, which is which maps each process to its proposal value. Let's say Y, which maps P to the decision value, let's say, right? And PC, program counter, PC, where maps from P to, let's say, a natural number. You have control in your program that goes from 0 to infinity. You have, let's say, you have program counter mapping each process to its the point in its program where the control is, right? And you have state, which maps P to anything. Let's say, for the sake of current example, let's assume, I don't know, natural numbers. No, not a set of natural numbers, for instance. Actually, you don't really care, so you just leave it. Let's say you keep it that way, right? Okay, so now we have defined system as a 4-tuple, right? X, Y, X containing X is a map that maps each process to its proposal value. Y that maps each process to its decision value. PC, which maps each process to the number, the control flow, essentially where in its execution the process currently is. And ST mapping each process to its local state, local internal memory state. Good so far? Okay, so this is good as long as you're doing local computation. But then this is a distributed system and you actually want to model messages and stuff as well, right? And how do you do that? Now, before even going there, right? You want system to start at a particular state. Let's say this is a system state, right? You want, let's say you have booted the distributed system, afresh. You just plugged in the system, and the system starts in an empty state. How do you represent that empty state? And let's say empty state here, as in not exactly empty state. Let's say it's the first transaction being agreed upon, right? So let's say a process we can think of. Let's say you have three nodes in your system. You can map, let's say, P1 to 0, P2 to 1, P3 to, let's say, 1, right? For instance, right? Which means that P1 is proposing to commit the transaction, P2 abort and P3 abort, for instance, right? Now, what would you map this? So this is X. Leave aside Y for a while, right? Let's say PC, you say that, okay, program P1 you map to its own control, let's say location number 2, P2 map to 4, and P3 map to 8 or something. Right? And state is also trivial. You can map P1 to some internal state. Don't care what it is. P2 to some internal state. P3 to some internal state, right? But the consensus has not yet been reached, which means that no decision value has yet been announced by any of the process, right? Which means you cannot map, let's say, if you want to come up with an initial configuration wherein no machine has decided a value yet, right? You cannot map in Y, P1 to 0 or 1, neither P2 to 0 or 1, neither P3 to 0 or 1, right? So for that purpose, you define, our model clearly is insufficient. You extend it by one special value, let's call it B, right? And start with the special value saying, okay, none of the processes have, have essentially decided on a value yet, have decided to either commit or abort it. So we'll represent it using a special value B. Okay, we have made one small extension to our model. Now let's go ahead further, right? We have so far captured each machine's state using its input and output values and its program counter and its internal state and its internal storage. So that's some aspect of the system. Like, what are we missing now?
The communication.
Communication, right? So we do not yet have communication. So let's say you have, okay, system state is, we have said X, Y, PC, ST. So again, the way we model this communication in the above example, right, using a message buffer, you can essentially adopt the same strategy here, right? You can now define a message buffer. Essentially, when I say message buffer, it is essentially a network, right? Think of network as simply a set of messages, right? Each message tagged by its destination process identifier. Right? So at any given point of time, network state can be represented by what messages are in flight, right? Which means a set of messages that are currently in flight, not yet been delivered. So essentially, message buffer is set of messages. So let's say 2 power MSG. MSG is a special value, for instance, a special type. You have M1, M2, M3 of type message, for instance. Right? So you have message buffer, which is essentially a set of messages. Okay, so that captures communication. You put a message, when a process has to send a message, it puts it in the message buffer. And when a process has to receive a message, right, it essentially removes that message from the message buffer and does the local processing, right? Okay, so we have modeled basically the network component and also the internal state components of this diagram, right? So we have, using X1, XY, PC, and ST, you model what happens here. And using message buffer, you model what's happened here, what happens here. So you're good. Good. Any questions so far?
I guess one quick question on the message buffer, is that 2 to the MSG?
Yeah, so 2 to the MSG, actually, okay, so it's a notation used to represent sets, right? So let's say you have, what is N?
Okay.
N is a set of natural numbers, right?
Right.
Now let's say you want to represent the set of all sets of natural numbers. How do you represent that? So the way to usually do it is, so here, this 1, 2, 3 belongs to N, for instance. You represent the set of, so 2 power N is set of all sets of naturals, which means 1, 1, 2, 3, etc. belong to 2 power N. So that's the notation we use. So here, when you say 2 power message, essentially what I'm saying is message buffer is a set of messages. No, it belongs to the set of all sets of messages, which means it's a set of messages, right?
Okay,
It's
cool.
not a single
Awesome.
message.
Thanks.
Yeah. Okay. If you feel not very comfortable with this notation, you should let me know now, because the proof and the rest of the class depends on this.
Did we not say that the message buffer will be represented by the process?
Oh yeah, go, very good. Yes. Okay, good. Okay.
Yeah.
Okay, good. Yeah, actually, that's a good point. Because we are modeling, when you think of message as essentially just message values and not including the destination ID, and you want the message buffer to contain, along with the message contents, also the destination process ID, right? If you're being even more specific, Prashant, so you can also model it as P cross messaging, as you have suggested. But I'm just dropping the first P cross because it's not needed for the rest of the proof.
Okay.
You could have as well done that, and it would still be okay. Okay, good so far?
Yeah.
Okay. Now what? Okay. So now we have defined what state, at a given point of time, at any given point of time, what the state of a distributed system, how it looks. You can model it using this XY list, right? Using this. Okay. State of system at any given point. Okay, but is it enough to just capture the state of the system at any given point? Since you're trying to prove a property about protocol, and what does protocol involve? Protocol involves not just the state, but also the control, right? So essentially you have to define a transition from one state of the system to other state of the system, right? So that is what is so far, we are missing. Does it make sense? Okay, so how do we define the transition system, right? So what is a transition system? So let's, so we'll define, let's say, transition system. Previously, we have said transition system is, let's call them state or configuration, right? Here, I think in the proof, they use the name configuration. So let me just use configuration. Okay. Okay, so previously we have defined, transition, the property of transitioning from one configuration, one state to another state, or one configuration to another configuration as a relation, right? So we have, let's say, design this config cross config, which means it relates to different configurations, which means you can go from configuration A to configuration B, right? But let's say this configuration, for a given config C0, right? There's all, let's say the system is deterministic, right? So given a configuration, given a message and so on. So there is, only one possible transition that it can take, for instance. Let's say for C0, let's say only C1 is a possible configuration, right? Then you need not actually define this as a relation, but directly define it as a function, right? So you essentially can define a transition between states as going from one configuration, mapping one configuration to another configuration, right? Okay. So let's move further.
Gautam, just to clarify, so
Okay.
if we have an idea of the model wherein if I exist in a current configuration C and I can move only to one other configuration from this place, irrespective of what happens. So then we represent it using a function. But if there was a possibility that I could move to multiple configurations from where I am,
right,
you would represent it as a relation.
That's correct. Yes.
Okay.
Yeah, because that's essentially what, that makes sense, right? Because a relation is essentially, relation can map, let's say there's a relation R that can map x2, 0 to x1, or a relation can relate x0 to x1, but it can also relate x0 to x2. But if you have a function f, right, f of x0 is always x1. If f of x0 is x2, then it must be the case that x1 must be equal to x2, right?
Okay.
So yeah. Okay. So you need transitions to describe this particular. You need to define what's exactly a transition and so on, right? So for that, I'm going to define essentially what is called a step. What happens in a step, right? So as I said, in the machine, the distributed system or any machine that you're capturing in a model has to execute step by step. So which means you have to define what constitutes an atomic step, right? So for the sake of this, to capture this particular system, I define a step as following. So essentially, or get a message, or receive, or read a message, right? Step at process P. Message from message buffer. Do local computation. Then send finite number of messages to other processes. So you can think of essentially as each step. So the system progresses in a stepwise fashion, and each step you think of system essentially selecting a process P, and the process reading some message that is intended to it from the message buffer. If there is no message intended, then essentially it reads an empty, it's some special value, for instance, let's say empty, right? So it reads a message that is intended for the process P from the message buffer, does some local computation, and as a result of local computation, it might generate a few more messages, finite number of messages, and it will keep those messages back in the message buffer, right? So you can think of each step as having basically 3 different phases. So the read phase, computation phase, and the write phase, right? So I define this as an atomic step, right? And system progresses as a series of atomic steps. So you have initial configuration, and then you take an atomic step, you get to the next configuration. Then you take another atomic step, you get another configuration, and so on and so forth, right? So that's how you model the fact that the distributed system is running from initial configuration, and you might reach some other configuration at some point of time. I mentioned initial configuration, right? Let's precisely define what an initial configuration is, right? So so let's say for a given process P, okay, let's just write it down. So so initial configuration has X, Y, PC, initial state, and the message buffer. So we define X as essentially anything, all the processes mapping to one of the values, So let's leave it unspecified for a while. Okay, let's just leave it like this. Right. Okay. I think I need to write out a little more clearly. Okay. So X is where a given process P any process can map to any of the values 0 or 1. So anything is a valid initial state. So when you have a consensus system, you can imagine system starting with, let's say you have 3 different nodes, right? Each node is free to propose either commit or abort, right? Which means initial state can map each of these nodes to either C or A or 0 or 1, respectively, right? So that's why I said, okay, for any P, or just maybe even more precisely, for all P gets mapped to 0 or 1. Okay. What about, so this is input, this is proposal, right? So what about Y? So Y is the decision value, right? We are just starting out. This is the initial configuration I'm defining. What would you map for each process P? What would you map its output in a decision value to initially? B, right? Because you haven't yet decided anything. PC could be one where you could start, when this process are just starting, you could map them to 0. And ST could be an empty set, for instance, right? And the message buffer could also be empty set because you're starting with a state where there are no messages in flight. Right? That is the initial configuration. Sorry. Okay, so that's the initial configuration, right? So this is initial configuration.
The message buffer is per process, right?
No, it's not per process.
It's global. Okay.
It's global because again, okay. So you want to, let's say, capture the fact that there are 2 messages in flight, one from process 1 to 2 with the message M1. Why is it slow? Okay. Another from, let's say, 2. There is something off with my system. Okay. 2 to 3 with them, for instance, right? So 1 to 2, 2 to 3. So you can capture this entire the 2 messages in flight using one single network state, which is message buffer. I'm calling it message buffer. It's containing 2 messages. If you expand it fully, you can write it down as 1 to M1 and 2, 3, M2, as Prash has suggested, taking source, destination, and the message. But for the sake of this example, this particular proof, we're going to leave out the source because it's not needed. So you just capture it as 2M1 and 3M2, right? The set containing 2M1 and 3M2, which tells you that the network is currently at a state where 2 messages are in flight. One destined to 2 with the value as M1, the other destined to 3 with the value as M2. Good so far?
Yeah, thanks.
Okay. Okay. I don't know why my system has gotten suddenly slow. Okay. So you map the initial configuration, right? Then what else? Let me check. Yeah. So what does an event? As I mentioned, so there's initial configuration, and then there is a step, right? So let me get the step. Go back to step. You have. Let me take it down. Okay. So I've defined a step, and as said, the system progresses in steps. So you want to represent this step. Like you want a way to say that, okay, there is a configuration C0, and then some step has happened. Okay. And now the system is at the configuration C1. Using X, Y, PC, and so on, you can represent C0 and C1. But how do you represent step? Right? So again, the step is a step at some process P, and it begins with dequeuing some message M, doing some local computation, sending more messages, right? So is there a way that you can think of that you can represent the step with?
Relation.
Okay, yeah, and what would it relate?
Well, the process and the message.
Yeah, so essentially a tuple, right? So it's not a relation because it's not actually, you don't have, relation is a set of tuples, right? You don't have set of tuples, you have a single tuple. So essentially a single tuple, you can capture this step as, for instance, P and M, where P is the process which executed the step, and M is the message that has been dequeued from, or not dequeued because it's not a queue, just read off from the message buffer, right? So let me restart the at least this process. The process has crashed. Now we have a faulty machine here. Let's see. Okay, this is fine. Okay, so you can represent this as step as PM, right? So in the proof, in the authors, the FLP authors have actually called it an event, right? So they give it a name as event, right? So each step is denoted as it's an event that's happening in the system. So upon an event, you take configuration C0 to C1, right? So you can think of, sorry. Okay, you can think of event E, right? E being applied to C0 to arrive at C1, right? So, or actually, let me move clear. So C1 is E applied to C0. You can think of it that way, essentially. So the system progresses, again, there's another event D prime, is P prime, M prime, to C2, and so on and so forth. Right, now you have completely captured the entire working of the system. You've captured both the state and the control, right? The state is configuration. You said you've captured precisely the configuration of the system. And you also captured the transition of control from one configuration to another configuration using these events, right? So essentially captured the entire workings of the system. Okay, so now we are in a position to actually, we have modeled an entire system and we can say something about the system and prove a few properties about it, right? And that's where we get to the part of, okay, now that we have known like what a system is and now we have what system we are talking about, you can state precisely using these artifacts we have defined what we mean when we say consensus is impossible. But before that, let's look at few properties of the system we have defined so far, right? So let me check my things. Okay. So first thing, so you have, so you have essentially Okay, let's go take a look at the initial configuration, right? So we have this initial configuration. So in this initial configuration, we have essentially hard-coded everything except X, right? So given two initial configurations, right? So what would they differ in? What could they be different?
In the first proposal, whether they propose a 0 or 1.
Right. So I could conceive one initial configuration, C0. This is different from that C0. Let's call it C init 0, for instance. C init 0 as mapping, let's say, first process to 0, second process to 1, and third process again to 0, for instance. So this is 1, and everything else is mapped to the hard-coded constants. And you can conceive another initial configuration where first process is mapped to 1, second is mapped to 0, and third is mapped to 0, with everything else again remaining the same. So this part is essentially the same here for both the initial configurations, right? So what does that tell you? So that means that if you have three, in this particular example, when I have 3 different processes, I can identify each initial configuration with a 3-bit number, right? So essentially, I can name this, I can number this initial configuration as 1, 1, and 0. 1. This initial configuration as 1, 0, 0, so on. Right? So how many initial configurations are possible here?
8.
8. So you have 8 possible initial configurations. So in general, when you have a system with P processes, P as in like the mod P is the set of process. So P mod P is the number of process. So there are 2 power P mod P possible initial configurations, right? And you can uniquely identify them by giving the P bit number. So P bit identifier for each initial config. Okay. So far clear. So you have full, the P bit space being occupied with 2 power P numbers, where each number essentially represents precisely 1 and only 1 initial configuration, right? Okay. So what can we prove? So let's write it down as an observation, right? So note 1, essentially, configuration is identified by P bit number. Okay, this is note 1. Let's make another observation, note 2. Okay, so let's say there is an event E, which is PM, right? So this is process P consuming a message M, right? Which means that the message buffer has PM in it along with other things, and you essentially, the event says that PM can be not dequeued again. It can be removed from the message buffer, consumed by process P to generate a few more messages that get added to the message buffer again. So that's what the event represents, right? So let's say there is an event E equal to PM that is applicable to certain configuration. So E is applicable to some configuration, C0, for instance. Okay. When I say applicable, what does that mean? Like, when can you apply an event E to C0, E being P and M? So if PM belongs to message buffer, right? So all that is required is equal to PM belonging to C0 dot message buffer, right? This is a rotation that I use to represent message buffer of C0. Right? So that's all there. So E is applicable to some configuration. C0 essentially means that message buffer of C0 essentially has that message stored in its buffer, right? The configuration has the message stored in its buffer. Okay, so E is applicable to some configuration E0, but what we do here, we play a game. We don't apply E to C0 immediately. We'll keep it aside, right? And then we let C0 take more steps using, by reading other messages or even by reading empty messages, right? So you have C0, E is applicable here, but we don't apply E. We're gonna let C take steps, some other, let's say E2, or let's not E1, let's start with E1. So E1 to C1, E2 to C2, and so on. And you have reached, let's say Cn, right? Is E still applicable to Cn?
I mean, if none of the events, if between them are equal to E, then it would be? Is that?
Yeah, so we have, so essentially none of the E1 to En are equal to E. We don't apply E, we keep it in the stash, and we let system takes other steps, and we reach a new configuration Cn from C0, right? E is applicable to C0, is E still applicable to Cn? Yes, right? Because no one's going to read that message from the buffer, it's still going to be in the buffer. So yes, right? So essentially what we say is, if an event is applicable to config C, then E is applicable to every successor of C, where successor is defined with respect to this transition, this step relation, right? So this is node 2. So that's this is node 2, right? Okay, we have so right now we are not aiming for the main theorem. We're just trying to understand the properties of our system, right? So that's why we're making small notes about what properties are true about our system. Okay. What else is true? Okay. So actually now we come to a somewhat significant property, which is stated as a lemma in the FLP that is required for the FLP theorem. So let's write down the lemma. Right. So which is commutativity of schedules. So a schedule, let me define. Schedule is a sequence of events. Example, sigma equal to E1 next up E2, so on, En, right? So when you say sigma is applied to some configuration C0, a schedule is applied to some configuration, essentially means that you apply E1 to E2 to En to C0, right? So essentially you stitch together multiple events and you get a schedule, right? So you can represent essentially C0 to E1 going to C1 ... to En taken to Cn as basically a single schedule, C0 going to Cn, where sigma is a schedule that contains, that stitches together E1 to En, right? Now the lemma, okay, let's define some other property of schedule. 2 more minutes. I'll define the lemma and then leave it. We'll come back next class and actually prove the lemma and go about proving the rest of the theorem, right? So let me just state the lemma and we'll leave. Okay, let's define, let's say, as I said, sigma is E1 dot E2 dot En, right? Let's say you have E1 is P1 M1 E2 is P2, M2, and so on, Pn, Mn, for instance, right? I define something called domain of sigma, a set of all processes that take part in that schedule, which is P1, P2, so on until Pn, right? Simple. So domain of schedule is essentially all the processes that have taken step in that schedule, in that sequence of events, nothing more than that. So now that we've defined this domain and the notion of schedule, we can state that the lemma, the commutativity of schedules, essentially as we start with the configuration C. Let's say I have two schedules, sigma 1 and sigma 2, one taking to C1, other taking to C2, and sigma 1, sigma 2 have nothing in common, right? Empty set. Right? So that is sigma 1 and sigma 2 are disjoint. This processes that have taken step to take from C2 to C1 are completely different from the processes that have taken step from C2 to C to C2. Now the lemma states that you can essentially apply sigma 2 to C1 and sigma 1 to C2 to arrive at a convergent value. Let's call it C3. So that is the lemma. So essentially, sigma 1, sigma 2 applied to C is equal to sigma 2, sigma 1 applied to C, which is why it's called commutativity of schedules, right? Schedules, the disjoint schedules are commutative. So that's the lemma, right? Okay, so we're going to discuss the proof for this lemma and why this is significant, and prove the rest of the lemmas in the main theorem tomorrow. But the key takeaway from this class is that essentially, we have covered the very first step of proving any landmark result for systems as complex as a distributed system, right? Which is to model precisely the components that we want from the system in a simple, the mathematics that is simple enough to let us do proofs, right? So that's what we have captured, and that's a key takeaway from this class. The proving theorems, etc., we'll cover in the next class. So I hope this makes sense. Any questions? I mean, any even general questions about like why they have done it this way, or where are we going with all of this, etc.
Yeah, I have one question about the last figure. So
Okay.
Does it mean like the ordering of the events doesn't matter? C will eventually reach C3.
Could you repeat the last part of your question?
Oh yeah, so it seems like the ordering of the events, if you take the left path or the right path, doesn't matter. So it will eventually reach C3. So I'm just wondering, like why the ordering of the events doesn't matter?
So here there's a key precondition for this theorem, right? Which is the disjointness condition.
Okay.
Yeah.
Okay.
So essentially, when you have, as I mentioned, so event, this goes back to our previous note, which I have written here, right? Note 2, which is that if E is applicable to C0, and you have C0 has taken multiple transitions wherein the same, that's the event hasn't yet been applied, so it is still applicable even after multiple transitions, right? Given that the same event has not been processed. So we extend that to multiple the schedule, which is a sequence of events, essentially saying that when you have completely disjoint set of processes that are taking step, right? So then what first set of processes do is not going to affect what second set of processes are. You can still, you can still execute the schedule that happened in the for the second set of processes, even after the first set of processes have taken steps. Right? That's what we say here. As an example, let's say you have a message. Let's say you have two processes, P1 here and P2 here, taking a step. So here P1 takes a step, and here P2 takes a step, right? By consuming a message M2, and here it consumes a message M1. So P1 might have taken a step, and it might have generated a new message for P2, let's say, right? But that does not prevent the fact that from P2 to now consume message M2 intended for it, right?
Hmm.
Which means the event E2 is that sigma 2 here is still applicable even after doing the first sigma 1. You understand?
Yes.
So yeah, so this disjointness condition is essentially what gets us to commutate. That's why we have the commutativity. That's why we don't. That's why the order doesn't matter among the disjoint events. Okay.
Thanks.
Okay. Okay. So that's all I have today.
Thank you.